Static electricity is the buildup of electric charge. Current electricity is the flow of electric charge. Specifically, we're going to define current electricity as the rate of flow of electric charge. Now, when I say that, know that I don't mean the speed of the charges. I'm not talking about how fast the charges are moving. I'm talking about how many charges are moving per second. The analogy would be cars traveling on the highway. You got a bunch of cars traveling on the Deerfoot. You're standing on the side of the road with your friend. One person, you've got a radar gun, and the radar gun, of course, measures the speed of the cars as they go by, and that's going to be measured in meters per second. Okay, speed is not how many cars you have, but rather how fast they're moving, how many meters per second these cars are moving. The analogy to electric current, however, is not the guy with the radar gun. The analogy to electric current is your friend that's standing on the side of Deerfoot with a stopwatch, counting the number of cars that are going by in a certain amount of time. So you measure the speed of these cars to be 27 meters per second. All right, good, that's V. He measures the current, or the rate of flow of traffic. He measures it to be 7 cars per second, or 3 cars per second, or 9 cars per second. Clearly, that's not speed. That's the rate of flow of traffic, 7 cars per second. You measured the speed, which was 27 meters per second. You can have a high flow of traffic. You can have 9 cars every second, but they can be going relatively slow, a relatively slow speed. And on the other hand, if it's the Deerfoot at 2 in the morning, you can have a very high speed of, let's say, 34 meters per second, but a relatively low rate of flow of traffic. 1 car per second, 2 cars per second, 0.4 cars per second, whatever the case may be. Do you understand the difference here? The current is how many cars per second are flowing. The speed is how fast they're flowing, the speed in meters per second. So we're not going to measure the current in meters per second, and we're not going to say it's distance over time. Rather, we're going to measure current, which, by the way, the symbol is I, a capital I, as charge over time rather than distance over time. It's not the number of cars per second, right? It's the number of coulombs per second. But it is a number of coulombs per second, just like the number of cars per second, not the meters per second. So charge is going to be measured in coulombs, of course. Time is going to be measured in seconds. So the units for current would be coulombs per second. Now, sometimes you see coulombs per second, but you sometimes also see the other unit for electric current. Does anybody happen to know what that is? Amps. We're not in chemistry class, or did you just know that?
We actually did that in chem today.
Just today? Wow. The unit for current is an amp, an ampere, or a coulomb per second. Exactly the same thing. Just like a Newton second is the same as a kilogram meters per second. Okay, just like, what's the other one I'm thinking of? Can't remember off the top of my head what the other one I'm thinking of is. So just like a Newton second is a kilogram meters per second, a coulomb per second is exactly the same thing as an ampere or an amp. All right, let's do a quick little example of this, and then we'll move on to the real topic at hand today, which is what happens when you have a current in an external magnetic field. This question says, what's the electric current in a wire if this many electrons flow through the wire in 7.5 seconds? The current is Q over T. Oh, wait, this isn't so easy, actually. Not as easy as we thought. We don't know the charge. What's the charge equal to? It's not 5 times 10 to the 10. If we have one electron that has a charge of 1.6 times 10 to the minus 19 coulombs, and we have 2 electrons Well, then we double that to get the amount of charge, right? 2 times 1.6 times 10 to the minus 19. Well, if we have 5.5 times 10 to the 10 electrons, then we're going to multiply the charge of the electron by 5.5 times 10 to the 10. So let's do that now. 5.5 times 10 to the 10, that's the number of the electrons you have. You multiply it by 1.6 times 10 to the minus 19 coulombs. That's going to give us a value of 8.8 times 10 to the negative 9 coulombs. So if we take that number and divide it by the time, 8.8 times 10 to the negative 9 coulombs divided by the time of 7.50 seconds. That gives me a current of 1.17 times 10 to the negative 9 units again, amps. Now, by the way, current we would say would be a scalar. There's no direction associated with it. Having said that, electrons can move this way or that way, right? We wouldn't say the current is a vector. We'd say the velocity of the electrons was a vector. Does that make sense? So current would still be a scalar, but the velocity of the electrons would be a vector. 1.17 times 10 to the negative 9 amps. Fairly straightforward, right? Not insanely easy, because we've got to do this to get the charge, but that's almost logical, right? If you have this many electrons and this is charged, then multiply them to get the total charge. Okay? Now, what happens when a wire, or any conductor really, that conducts electricity, is exposed to an external magnetic field? What happened when a charged particle is exposed to an external magnetic field? It experienced a force. And in the end, that force on that charged particle ended up being ended up causing it to go on a circular path. That doesn't happen with wires. The wires that are exposed to the external magnetic field don't go in a circular path. Let me just draw you a picture to help explain what does happen. If I had an electron moving to the right, I'm not going to draw the velocity of this because it's going to end up getting too cluttered, but remember that this is moving to the right. This would experience a force. Here, I'll draw a little arrow there. It's moving to the right. It experiences a force downward. Now, don't worry about what happens to it. It ends up going down and ends up going in a circle. Don't worry about that right now. Okay, at this moment, it experiences a force downward. What if I had another electron also moving to the right? Well, it would also experience a force downward. Well, what if I had another one also moving to the right? It would experience a force downward, and so on and so on and so on. Okay, if I have a million of these things all moving to the right, then they're all going to experience a force downward. In fact, they're all going to want to go in circles, right? But what if those electrons are moving to the right are all inside a wire? Well, they all still experience a force downward. But now they can't go in a circle because they're in a wire. They can't physically go in a circle because they'd have to leave the wire in order to go in a circle through the magnetic field. So they're all being pulled downward, but they can't go in a circle. So the net effect of this is that we get a force on the wire acting downward. That is really just a combination of the force on all of the individual electrons going through a wire. Does that make sense? The force on the electron, well, we've done that, right? The force on the electron is F is equal to QVB. But we're going to give you in just a second an equation that describes the force on the wire itself as well. I mean, technically, you could add up the force on all of the individual electrons to get the force on the wire. But there's a nice simple equation that gives us the force on the wire as well. So I'll show you what that is in just a moment here. Current carrying wire consists of moving electrons in a conductor, as I just showed you in the diagram. Usually a wire. It doesn't have to be a wire, but some kind of conductor. Now, electrons moving through the magnetic field experience a force, according to what we just said. F is equal to QVB. So, because each of these individual electrons experience a force, well, then the wire itself will experience a force as well. the same as the force on the individual electrons. But remember that it's not going to go in a circle. It can't. The wire can't go in a circle. The charges inside would like to go in a circle, but they're bound inside that nucleus. So it's like you're walking down the hallway, a narrow hallway, and you want to turn and go in a circle, but you can't, because when you turn to go in the circle, you hit the wall of the hallway. You can't physically go in a circle. All right, how do you think you find the direction of the force on this wire? Same way as we found the direction of the force on the particle, right? Charged particle moving through a magnetic field, we use the hand rule for deflection. Do the same thing. We're going to stick our thumb in the direction of the electric current. So if the current's going to the right, then our thumb goes to the right. Our straightened fingers go in the direction of the external magnetic field. Not the magnetic field that's caused by the wire. There is a magnetic field caused by the wire. It's found by the wire grasp rule. But that's not the one we're talking about. This is the external magnetic field. Our palm will point in the direction of the magnetic force. So this isn't any different. If you can find the direction of the force on a single electron inside that wire, then you've got the force on the wire itself, because all the electrons experience a force in the same direction. All right, how are you going to find the strength of it? The magnitude of it. Well, the magnitude of the force on a single charge was QVB. The magnitude of the force on the whole wire is, what do you think it's dependent upon? What do you think is going to affect the strength of the force on the wire? You guys told me last week what affects the strength of the force on an individual charge. It was the magnitude of the charge, Q, times the speed of the charge, V, times the strength of the field, B. F is equal to QVB. What do you think affects the force on the wire itself? What did we just do a few minutes ago? What did we just learn about? It seemed to be kind of like, why are we learning this in magnetism? Yeah, the current. And the stronger the current, the stronger the magnetic force. It makes sense, right? You get more current, it's going to produce a stronger magnetic field, which is going to interact with the external magnetic field stronger and produce a bigger force. What else do you think is going to affect it? Sure. The magnetic field strength, yeah. The strength of the field, the stronger the magnetic field, the stronger the force is going to be. We're missing something, you can tell in the middle there, right? It does need to be perpendicular, but what needs to be perpendicular? The length of the wire. The longer the wire you have, the stronger the magnetic force. And Kashi, we are going to put a little perpendicular sign there, because the wire needs to be perpendicular to the magnetic field. If it's parallel to the magnetic field, what's the force? 0. If it's perpendicular, it's F is equal to ILB. If it's not perpendicular or parallel, there is a force, but we don't need to worry about that in Physics 30. So let's identify what each of these means. This means the current, and that's going to be measured in amps. This means, now, careful here, this means the length of wire that is perpendicular, again, that word, it's going to appear several times in this unit and the next unit, perpendicular and exposed to the external magnetic field. So in other words, if you have a wire that's parallel, don't count it. If you have a wire that's perpendicular, count it if it's in the magnetic field. Got it? If it's outside of the magnetic field, don't count it. And that's going to be measured in meters, by the way. And this is the external magnetic field. And that's going to be measured in Tesla. So for instance, let's say we have a magnetic field like this. Okay, there's my magnetic field pointing to the right. I have a wire like this. Okay, this is going to be This is going to be 10 centimeters. This is going to be 10 centimeters. This is going to be, from here to here, is going to be 8 centimeters. And this is going to be 10 centimeters. What length would we use there? What's the length of the wire here? 10, 10, 8, 10, or some kind of combination of those? What is it? It's just 8. Yeah, the only thing we'd use there is the 8, because we're looking for the part that's perpendicular to the magnetic field, which takes away this and this. And we're also looking for the part that's in the magnetic field or exposed to the magnetic field, so we take away this. The length of that wire would be 8 centimeters, although we'd have to convert that to meters, right? Here's our example, number 2. It says a 10 centimeter long length of wire, circle that because we want to be in meters, carrying into the page lies in the magnetic field pointing towards the left. Those are perpendicular, right? Perpendicular, so that works. This many electrons flow through the wire in 10 seconds. What's the magnetic force acting on the wire as a result of the magnetic field? All right, so we know that F is equal to ILB. We don't know what I is, though, so let's find I. I is equal to Q over T. That's what we learned first in this lesson. Oh, we don't even know what Q is, so let's find that. Q is the number of electrons, 8.0 times 10 to the 19 times the charge of an electron. That gives us a charge here of 12.8, which we're going to divide by T. We get 12.8 coulombs divided by the time here of 10 seconds, which is 1.28 amps. And now that I have the 1.28 amps, I can sub that in over here. The length of the magnetic field here is 0.10. The strength of the magnetic field is 2 times 10 to the negative 2 Tesla. And we multiply those together, we get 2.56 times 10 to the negative 3 newtons. Now notice it doesn't say the magnitude of the force, it says what's the force. So we need a direction here, right? The electron current is going into the page. The magnetic field is pointing to the left of the page. So we're going to say thumb in the direction of the particle, into the page. Fingers field to the left. Which way is my palm point? Notice which way is my palm point? Down the page, yeah. So 2.56 times 10 to the negative 3 newtons down the page. Another term for this is called the motor effect. This is how an electric motor works in principle. You apply an electric current through a wire that's exposed to a magnetic field, the wire moves. And there you can cause wheels to move, or a drill bit to move, or the bristles on your electric toothbrush to move as a result of that, the motor effect. All right, that's it for today.